Welcome to the part 4 of the tutorial series on reinforcement learning in Godot. In this part, we will implement ground nodes and resetting the environment state. Let's go back to the environment node and add the child rigid body 2D node. Rename it to ground. We changed the node to static because it does not move during the episode. We add a collision polygon to it that will generate later. Also add polygon 2D to visualize it. Next, we add landing area, the area to denote and call it landing area. To it, we will attach a collision shape to Z to detect touchdown by the lander. The collision shape will be a rectangle with the sizes 50 by 10. Also, let's hide the lander node for now and move the ground to the center of the screen. Oh, we misparented the landing area. Now we will start generating the ground collision polygon. Let's attach a script. First, let's write a function to generate the polygon corresponding to the ground. We will pass the number of vertices the ground will have and the height of the terrain. We will create a variable for the polygon, full vector to the array. Next, we get half width of the landing platform from the landing area collision shape size. Then our polygon will start with the two vertices at the edges of the landing platform. The platform y-coordinates will be at the ground height. Our strategy is to generate half of the terrain, then just repeat the same for the second half. Create a new function generate half that will take the array to which we will add the vertices, the number of vertices, and the parameter left-right, that will be -1 for the left part and +1 for the right one. During the generation, we'll add delta x and delta y to the previous vertex coordinates. The randomization scales will be 10 for delta x and 100 for delta y. The average polygon displacements along x-axis, dx, will be viewport width divided by the number of vertices, and the initial vertex position will be init_x. In the loop over the number of vertices, we generate x, initial x, plus I times dx times left-right coefficient, plus randomization part. Similar for y, but we take the previous vertex y and add the randomization. Now we check if we go below the ground height and cap it to 5 pixels above the ground height. Also, if we generated x too close to the previous one, we also cap it to 5 pixels. Then we add vertex to the array and return it. In the generate ground function, we now add the left part to the terrain first. We pass our polygon variable, half the number of vertices, and -1 to the left-right coefficient. Now we invert the array so that the first vertex will be the one to which we add the right part. Afterwards, we add the bottom of the terrain to complete the collision polygon 2D. It will be 3 vertices. Last polygon x height of the terrain, then polygon x 0, and finally first polygon x 0, and then return the final polygon array. Now we fix some mistakes and move on to the node initialization. We clear the collision shape of this object, then we generate grounds with 20 vertices and 150 height. Then the shape will be a concave polygon shape 2D. We then convert our vertex array into segments by pairing together neighboring vertices. Now we pass the segments to the shape. Finally, we register our shape in the rigid body node. Now we want to visualize our collision shape. We set polygon of the polygon 2D node to ground. We set its color to black. Then we place our landing area to 0, -150. Then we want to let the parent node know where the landing area is. So we define a variable area center and assign global position of the landing area using our ground node transform. Finally, we call update. Then let's try to run the codes, and we have a bug. First of all, we don't have any shapes assigned by default, so we don't really need to clear them. We also don't need collision polygon 2D because we directly add a shape to the rigid body 2D. Also, we have to add shape index to the shape registering function. Now we run the code and we see that the ground is in the center of our screen. So we have to move the ground to the bottom of the screen. Finally, let's work on resetting the environment. First, we'll make ground and actor nodes their own scenes. We go to the environment script, and instead of statically define children, lander, and ground, we define variables for these two scenes and add a new function reset. We also will be resetting on the initialization of the scene. In the reset function, we check if these two scenes already exist and free them. Now we need to preload the scenes. We then instantiate them and assign to our agent and ground variables. We add to the environments as the children. Then a fixed number of mistakes. Let's remove the scenes from the environment node and then run. So we can see our lander, but before we fix that, let's set the ground transform to the center bottom of the viewport. Same thing with the lander, but we place it at y equals 100. After fixing stupid mistakes and running again, we still can't see the lander. Turns out I forgot I made it invisible. Let's run the environments again. Now we have ground and agent, but they do not interact, sadly. After some time, I figured we overcomplicate everything, and we will still use the collision polygon 2D. In the ground script, we just use function setPolygon with our ground array as an argument. And now everything just works. Let's make some small visual changes to our ground and the landing area. First, let's turn off the visualization of the collision shapes. Then let's draw the outline of the ground with a white color, line width 2.0. We just iterate over the polygon and draw the lines. Now let's draw 50 by 50 flag with a transparent background and export it to PNG. In the editor, just drag the flag to the landing area, resize it, and move them to the corners of the platform. And let's move them up half the height of the collision shape. Perfect. Finally, let's randomize the agent positions upon the reset. It will be placed between 100 and viewport size -100. And just to be cautious, if the agent and ground existed before reset, we will remove them from children before freeing. After we bind environment action tensor, first component, to the resetting of the environment. In the Python script, let's reset the environment every 100 steps for testing purposes. Do not forget to activate torch on the environment and run the Python script. Okay, we forgot to export our updated environments. Do just that and rerun. And we see that the environment is reset at every action step. Turns out we had two bugs. Obvious one with the if statement and not so obvious one. Because the tensors in the shared memory are persistent, when we tell our environment to reset, the corresponding tensor remains constant on the next step. We need to pass zero environment action tensor at each action step to alleviate this. Now everything works, and see you in the next part.